Okay. Hello and welcome everybody to our Astro Lunch series. It's my pleasure to welcome Drew Jamieson. In fact, welcome him back to Waterloo. Let me start. I think it's an interesting introduction for me. So I'm just going to walk you through a couple of stories. So if you are lucky enough and you get old enough, students you happen to work with then happen to become professors of their own, and you're lucky to introduce them to audiences. So I was thinking I would introduce Marlena Loverda today, but unfortunately her son was not feeling very well. So it turns out if you're even luckier and you're old enough, you get to introduce the students of the students you got to work with. And I've become successful. And in this case, that's Drew, who's worked with Marlena Loverda, the PhD student at Stony Brook. And as it turns out, in such a small world, Drew happened to be a student in the first class that I ever taught at UW. It was in quantum field theory in 2011. And he was a very good student. He was at Guelph, but as you know, we have this joint program. I went and checked, he got 98 out of 100. So he was a very a top mark there. That's very good. And of course, he continued to do exciting things. He ended up in China, as he was telling me, teaching physics to high school students for 2 or 3 years. And after that, he came back to North America to do a PhD with Marlena Loverda at the Stony Brook. And he's been doing exciting research in numerical cosmology over the past few years. And next year, he'll be done with his PhD and will start as a postdoc at Max Planck Institute for Astrophysics in Germany. Today, Drew is going to tell us about large-scale structure in a separate universe, and take it away, Drew.
Great. Yeah. Thanks so much for that very thorough and flattering introduction. I'm a PhD student at Stony Brook, as Nayesh said, and my research focuses on large-scale structure and n-body simulations, which is what I'll be talking about today. I'm really sorry my advisor, Marlena Loverda, couldn't be here instead. Her little 4-month-old isn't feeling well today, so I will do my best to give my version of the talk that I think she would have given. So just as an overview, I'll review some of the goals and challenges of using the large-scale structure of the universe to do cosmology. And then I'll present the separate universe technique and explain how it can be used to address some of these challenges, large-scale structure analysis. And I'll show some examples from my own work of the separate universe technique. And then finally, in the last part of the talk, I'll present some new observables, which my advisor and I have been studying more recently, which were motivated from the separate universe point of view. So in large-scale structure, we have many ongoing and upcoming surveys, which will, over the next decade or so, provide us with this enormous data set, mapping out the positions of the galaxies throughout the universe. And we hope to do many things with this data set. We hope to learn about dark energy. We hope potentially to constrain or detect primordial non-Gaussianity, say, which can help us learn things about the early universe and inflation. And maybe even weigh the neutrinos, detecting the sum of the neutrino mass through the effect that neutrinos have on the large-scale clustering of matter. So these are some ambitious and important goals, and we'll have a huge data set to try and meet these goals, but there are a lot of challenges in connecting what we can observe with ultimately what we predict for cosmology and for large-scale structure. So on the prediction side, typically we start with something like a model of the early universe, like inflation, which gives us a prediction for a set of statistical fluctuations among the primordial density field. So for example, I can have a curvature mode and its endpoint statistics. Maybe I'll also have an isocurvature mode present in the early universe, and that can cross-correlate with the curvature fluctuation and have its own autocorrelation functions. And so these primordial fluctuations then imprint themselves onto the various components of the cosmological fluid, which evolve deterministically according to the expansion history of the universe, according to gravity, and according to the Boltzmann equation, which is sensitive to the different contents of the universe. In a linear regime, we describe the fluctuations of these different components of the cosmological fluid in terms of transfer functions, which encode some of this information about gravity and the expansion history and about the different contents of the universe, and also these sort of sources of primordial fluctuations, which encode the information from the early universe. And ultimately, we can predict the late time statistics of, for example, the matter field, which is what we're interested in large scale structure. So the power spectrum, the bispectrum, these endpoint correlation functions. And in the nonlinear regime, we can achieve sort of the prediction for these fluctuations by using n-body simulation models. And so we're hoping to extract from these endpoint correlation functions this information about the contents of the universe and about the early universe. On the other hand, we observe much more complicated objects. We observe things like galaxies, or maybe we use our galaxy catalogs to try and find voids, or we do intensity mapping or weak lensing. And so these are all fairly complicated nonlinear observables. And what we want to do is relate these complicated observables to the things that we can predict, to the sort of fluctuations in the matter field and the statistics of the fluctuations in the matter field. And one strategy for doing that is just by smoothing over large enough patches of the universe. So, determining the number density in large enough patches and the fluctuations in the number densities in those patches for galaxies. And in that case, the fluctuations in these number densities are related to, in a simple way, the fluctuations in the matter field. In really linear scales, they're just proportional to each other. And the proportionality factor here is known as the bias. So if I cross-correlate galaxies with matter, I would have a bias coefficient and the matter-matter correlation function. Similarly, the galaxy autocorrelation function has this bias factor squared, and I might have higher order terms if I have a higher order bias expansion. So it's very important to have ways of understanding and modeling these biases, because ultimately, the new and interesting physics that we're hoping to detect and constrain, the effects of that new physics may be fairly small. And so we need really robust and accurate predictions for our observables. And so in summary, we have these things that we can predict, such as the configurations of the matter field using either perturbation theory or simulations. And we have these complicated things we observe. An example of how to connect these things, for example, like for the power spectrum, which is an observable we're really interested in. I plotted here, the solid curve is a linear power spectrum, which is used to generate initial conditions for simulations that I run. And then the blue squares here are the measured power spectrum from running this n-body simulation. And it agrees really well in the low K regime, which is the linear regime. And then you can start to see the effects of nonlinear clustering, which is why it disagrees up here. But if I measure in my simulations things that are more similar to, say, galaxies, things like dark matter halos, then I find that the power spectrum, the cross power spectrum between the matter and the halos is just systematically higher. And so this is this biasing effect. On the right-hand side, I'm showing similarly this linear power spectrum compared to a number of different sources of data. This is kind of an older plot now, but it has the dark energy survey, also galaxy surveys from SDSS and BOSS. But you'll notice that on the very largest scales, currently really all the constraints come from the CMB, from the Planck mission. In the future, what we're hoping to do is improve on these with our large-scale structure observations and detect potentially new physics up here where the constraints are not really that good from the CMB, because there's only so many modes that you have on these large scales in the CMB. And so it's important to understand where this bias comes from and how to model it or how to calibrate it using, for example, simulations. And so to explain this, here is a slice through an n-body simulation for the matter field. So the bright regions are where there's a lot of matter, and the dark regions is where there's not so much matter. And then I can run a halo finder on this matter field and find the positions of the high density peaks, the sort of virialized collapsed objects in the simulations, which are the environments in which galaxies are going to form. And so you can see here the bluish circles are the positions of these halos, and they closely trace out the brightest regions of the matter density field, as they should. Similarly, I can then run a void finder on this halo field and find the positions of cosmic voids in the halo field. And so those are shown here as the yellow circles, which correspond to the really underdense patches of this density field. And so you can see in this overdense region, I get a ton of halos, not very many large voids, a few small voids. Whereas up here in this underdense patch, I find quite a few large voids and sort of a whole hierarchical structure of voids and voids. And so what's going on here is that I really have some long wavelength density perturbation, which is modulating the structure formation locally in different regions of the universe, depending on whether or not they're underdense or overdense patches of the universe. So in this underdense patch, I find systematically just fewer massive halos. I find more large voids, fewer small voids actually. And if I just measure the power spectrum in this little box alone, then I find it systematically has a higher amplitude. Similarly, for this overdense patch, I find more massive halos, fewer large voids, more small voids actually, and higher amplitude for the power spectrum. And so this effect of long wavelength perturbations on small scale structure formation is exactly what we're trying to explain, or exactly what we're trying to sort of describe using the separate universe approach.
Sorry, can I ask you something? When you say the larger or smaller power spectrum, are you talking about power spectrum of galaxies or power spectrum of matter?
Yeah, the matter power spectrum. So the matter power spectrum, if I just measured it in this sort of sub-region of the universe alone, will be different from the power spectrum globally. In a way, I'll sort of explain this later, in a way that it really corresponds to the squeezed limit of the bispectrum, which is the response of the local power spectrum to this long wavelength perturbation. It's a coupling between small scale modes and a long wavelength density perturbation.
And this is because of non-linear clustering effect?
Absolutely, yeah.
Okay,
it's sort of a weakly nonlinear effect.
Thanks.
So from the separate universe point of view, I have a really long wavelength density perturbation. From the point of view of a small scale observable who only really has observational access to this small region of the universe, this long wavelength perturbation looks like a shift in the mean density of the universe. And so I can define sort of this locally defined separate universe mean density by absorbing the long wavelength mode in its local value in this patch of the universe. And what this does is it sort of makes this patch seem like its own separate universe with its own set of cosmological parameters. So it has a local expansion history, so a local scale factor and a local Hubble rate, which differ from the global expansion history in a way that depends on this long wavelength mode and its evolution. And one really nice thing about this is that because it's a long wavelength mode, it's well within the linear regime, and I can just compute this evolution using perturbation theory. What that allows me to do is to define a set or a pair of separate universe expansion histories, one corresponding to the overdense patch, one corresponding to the underdense patch. And then I can measure any observables I want in these two different simulations and determine what the linear response is of this observable to the presence of this long wavelength mode, which is this sort of nonlinear coupling between this long wavelength physics and the small scale structure formation. And so this method has been used to study many different observables. So the power spectrum, as I said earlier, if you measure the linear response of the power spectrum, what you really get is a sort of angle averaged squeeze limit of the bispectrum. Similarly, if you measure the halo mass function in a separate universe, its linear response corresponds to the halo bias, the linear halo bias. And I will describe some work I did looking at the void size function, which gives you the linear and void bias in the separate universe. And later on, I'll talk about one-point statistics from the point of view of the separate universe, which is more recent work that I've been doing with my advisor. So just as a sort of a simple example of how this works in practice, if you measure the halo mass function in an overdense or the global cosmology or an underdense cosmology, you find that there's different halo mass functions you get. So this is the number density of halos greater than some mass threshold as a function of that mass threshold. And in the overdense simulation, you just get more massive halos. In the underdense simulation, you get fewer massive halos, and the fractional difference between these gives you this bias curve. So the massive halos are highly biased, and the more low mass halos are essentially have a bias of 1 nearly. And so more traditionally, you would compute this as the clustering bias, which is this ratio of the halo matter cross power spectrum to the matter matter power spectrum, and look in the sort of linear regime in the low K limit, which corresponds to this separate universe response, which we compute as a finite difference derivative of this halo mass function with respect to the long wavelength mode. And so I should say this method was originally proposed in these papers here, and these results are from my own simulation, but sort of just reproducing their results. Some work that I did with my advisor, which is in this paper here, is looking at the same effect for voids. So this is the void size function. So the number density of voids above some given effective radial size threshold in overdense global and underdense cosmology. And so you can see you get systematically more large voids in this underdense cosmology. It's hard to see here, but these curves cross. It's on the logarithmic scale. And so you actually do get more small voids in the overdense cosmology. And so you get this bias curve here, where you get strong negative bias for the large voids and sort of a weakly positive bias for the smaller voids. And again, this would correspond to, and we checked in this paper that does actually equal or agree with the results you get from the clustering method of taking this ratio of power spectra and the linear regime. But in fact, one of the advantages of the separate universe approach is, as you can see, there's some, we run many simulations and average over them to get some confidence interval, some error for this bias. You get a smaller error using the separate universe technique than you typically do using the clustering method. And so that's one of the advantages.
Hi, Drew, can I ask you something? I'm not a cosmologist, but so why this bias is always larger than one for halos and smaller than one for voids? I mean, for the simulations, you can get it, I guess, numerically, but you have some sort of intuitive way of understanding it from this coupling of the long modes to short modes. Is it easy to understand?
Yeah, is it easy to understand? A good question. So the bias is in some sense, the bias is kind of telling you about the rarity of objects. So the bias has to do with nonlinear clustering. So basically the halos form, but then the halos themselves fall in together and cluster together. And so the bias is really telling you about sort of the excess clustering of these nonlinear objects with respect to the matter field. And so basically you get really large biases for these really rare objects because, I don't know about a really intuitive way of explaining it. Essentially, you have this fractional difference between these bias curves, but you're really taking this like logarithmic derivative, right? So the denominator here is getting really, really small, while the difference is also increasing between these curves. And so that's driving this bias up. So it's really the enormity of the bias here is telling you about the rarity of these objects, which is saying they're more sensitive to the long wavelength modes because you get many more of them in an overdense patch compared to an underdense patch. Whereas for smaller mass objects, you don't really get significantly more of them in an overdense patch compared to an underdense patch.
Okay.
Does that answer your question? So, and then similarly for the voids, in an underdense patch, you just have less matter around, so you have more opportunity for forming large voids. And also the underdense patch is actually expanding faster. So those voids are getting larger than in an overdense patch or in the global universe. So you're going to find many more large voids, which is this sort of modulation of structure formation.
I see. Yeah, but since I mean, naively, since I would have expected that you will have long wavelength modes that give you more power on a specific small box, and some of them give you less power in a specific small box, then in the end, the bias will have been just one overall.
So actually the more power, I understand what you're saying. The more power actually kind of explains why you get more small voids, right? So you were right, you get more power, which means your density contrasts are more extreme. So the underdense regions of an overdense patch, which is, it's kind of hard to keep track of, but those regions are actually getting depleted more in a more extreme way, but they're smaller in size. So you get sort of more abundance of these small voids, and the voids may be deeper or maybe have in their profile have a sharper drop off in the overdense patch. So the void profiles are really sensitive, but you're not going to get extremely large voids in an overdense patch.
Okay.
Does that make sense?
I guess. Okay, thank you. I'll just let you move
on. So actually, I mean, on that point, I guess I can think of a very large void as just the inverse of a very large halo, right? Because all I'm doing is switching the sign of delta, right? The sign of overdensity.
Yeah, it's a little more complicated in terms of the nonlinear evolution because halos collapse and virialize, whereas voids, decouple from the expansion by expanding faster and faster. And so the important thing is really the velocity divergence of the void. So their physics is a little different in a nonlinear regime. Okay, so some more advantages that I said, you can get sort of a cleaner measurements of these bias coefficients using the separate universe method. In addition to this, there are other advantages, such as, for example, As I said, you only really need to know the evolution of a linear perturbation, which you can compute using perturbation theory. All of the small scale physics is simulated using standard n-body codes. So I don't need to modify some n-body code in some significant way to do this. And I can also include beyond lambda CDM physics through the effects that this new physics have on long wavelength perturbations. So examples of this are looking at scale-dependent bias effects from massive neutrino cosmologies, or scale-dependent bias effects from dynamical dark energy models for adiabatic perturbations. What I'll present next is some work that I did with my advisor looking at isocurvature dynamical dark energy perturbations, which I'll explain in the next slide, and scale-dependent bias effects in that scenario. More recently, I've collaborated with a fellow PhD student, Charwish Shiv-Shwarkar, to look at instead of beyond lambda CDM effects, this is radiation effects on bias, which is within lambda CDM, but are sort of different than the typical biases that people look at. I'll briefly discuss these results as well. So for this application that I looked at with my advisor, we decided to consider a dynamical dark energy model with a scalar dark energy field, which is, so the scalar field is sort of responsible for the dark energy, for the accelerated expansion of the universe. And this scalar field comes with a sound speed. So there's some dynamical pressure that this perturbations in the scalar field have. This model was first actually looked at by Gordon and Hu earlier, looking at the effects of this model from the point of view of the CMB. And we looked at the effects on large scale structure and scale dependent biases. So in this plot, I'm showing the time evolution as a function of scale factor of fluctuations in this dark energy field over a range of different scales. So 1 h0 corresponds to a wavelength the 10th of the horizon scale, and 100 h0 is the smallest one on this plot, which is 100th horizon scale. And so as you can see, the perturbations at early times and outside of the horizon are all sort of constant and frozen. And as they cross the horizon, as they approach the horizon scale, they enter and start to grow. So this model has some clustering dark energy. But because there's some dynamical dark energy, they eventually approach the gene scale and become pressure supported. And so they oscillate and decay eventually. And so for this smallest scale mode of this plot, this mode has become completely unimportant for structure formation at late times because it's almost entirely decayed away. And in fact, it was never really that important because when it was most significant was deep into matter domination when the dark energy isn't that important anyways. On the other hand, for the other extreme, for this horizon scale mode, it really hasn't, it's only just entered the horizon, so it hasn't really had an opportunity to grow yet and affect structure formation in any significant way. Whereas in between these two scales, we find a mode which has crossed the horizon and it's only just crossing the gene scale today. And so it is, as big as it could be today, essentially, and has maximum opportunity for affecting small scale structure formation. Now, these fluctuations in this dark energy field are totally independent from the usual fluctuations in lambda CDM, which are the adiabatic fluctuations. And so the matter perturbations are sourced both by these isocurvature dark energy fluctuations and the adiabatic fluctuations. And so I can consider both different configurations, say the ratio of I over R here is 100, or over here it's minus 100. And I can look at different scales for these long wavelength modes, and I get different growth histories for matter perturbations. So again, this K equals 100 H0 mode is essentially the long wavelength mode in just standard lambda CDM. And it's really the same on both plots. They have different horizontal axis scales. Vertical axis scales. And so this is essentially the regular growth history for long wavelength modes in lambda CDM, which is independent of scale in lambda CDM. On the other hand, for this really large scale mode, which is horizon scale today, it has this really reduced growth because the most important component of it is the isocurvature component, and it hasn't had much opportunity to grow yet. So it sort of has a suppressed growth early on and has to grow a lot late in order to catch up because I fixed the final value. And then finally, for this gene scale mode, today, it has radically different growth histories depending on the configuration of isocurvature and curvature fluctuations. And so you can see this has sort of a huge scale dependent effect and huge effects based on the configuration of these modes. And so I can use any one of these to define a pair of separate universe cosmologies and determine what the contribution of the halo bias is for this mode or this mode or this mode. And so these results for the halo biases are what I'm showing here as a function of mass.
Sorry, can I ask you something? I think I'm a bit confused about this. so your modes can propagate in and out of the box if you have a finite sound speed. Isn't that the problem?
So the really long wavelength modes, the way the separate universe is sort of set up, we're really only considering a patch which is much smaller than the size of the modes. So like the velocities on these really large scales are not very significant. So these perturbations are not really traveling around very much. They're really just kind of growing in this local sort of smaller patches within the environment of this long wavelength patch. So
okay, yeah, it's a little bit confusing because, I mean, for CDM it's kind of clear that, okay, so I mean, there's sound speed is 0, so if you have an overdance patch, it's kind of decoupled if it's big enough, that we have a big enough box, it's decoupled from the rest of the universe. But if you have a finite sound speed, I mean, it's a little bit harder. I don't know if you have thought about that, or you think it's not really an issue that there's the finite sound speed.
Yeah, I don't. So there's a paper by my advisor and Wayne Hu and some of their collaborators called something like Separating the Universe into the Real and Fake, where they go through this analysis with these kind of more complicated models with finite sound speeds and entropy and stuff like that. And what they show is basically just from the Einstein field equations, if you separate out long wavelength perturbations and then try to reabsorb them in this sort of separate universe sense, you do really recover something that looks like the Friedmann equations.
Okay.
In this case with finite sound speeds, it's not a Friedmann equation with, say, a constant curvature. It's a Friedmann equation with a curvature that looks like it evolves. So it looks like it has some sort of exotic form of energy density that is hanging around. So you can't do this just by shifting cosmological parameters. You really have to compute the evolution of these long wavelength modes and then compute the corresponding expansion histories by hand.
And that's what you do.
Yes, and that's what I do.
Cool. Thanks.
Yeah. So yeah, for these halo biases, we get effects that depend on both this configuration of isocurvature and curvature, and effects that depend on scale. So again, we have this, the most striking effect is for this gene scale mode, which sort of has this enormous bias when I over R is plus 100. Again, the bias curve for the solid green curve is the same on both plots, and it's essentially the standard lambda CDM bias curve. And so this is really nice. We can characterize these effects using separate universe simulations, again, without needing to significantly modify an n-body code to incorporate this complicated dark energy model as some, say, effective fluid description or something like that. But not only that, we can actually motivate really accurate models for these scale-dependent bias effects from the separate universe point of view. So to explain how that works, if I imagine that the halo mass function is some universal function of the power spectrum. So the abundance of objects that you get depends on sort of the initial power spectrum you have. Then what you would expect is that the bias, which is the response of the halo mass function, would be proportional to the response of the power spectrum. And the nice thing about that is that I can just compute the response of the power spectrum using perturbation theory. I don't need to run simulations to measure that. If that is true, then what I should find is that if I take the ratio of any two bias curves, the mass dependence should cancel out. And I should be left with some quantity that depends on scale and potentially depends on this configuration of I over R, but doesn't depend on mass. And it is predicted by the ratio of the power spectrum response in the separate universe. And this is exactly what we find. So this plot shows the ratio of bias for different scales and for different configurations of I over R, compared to the bias that you get in just regular lambda CDM with adiabatic perturbations. The red dots are the simulation results, and the white curves are the model prediction, which is just the response of the linear power spectrum, taking the ratio over different scales, different configurations of I over R, and comparing that to the power spectrum response when you just have lambda CDM and adiabatic fluctuations. And so you see there's like excellent agreement for this scale dependent effect, given this really simple model. And so the reason why this is significant is because if I wanted to use data to try and constrain the model parameters here, one might worry that I have to run tons of simulations to characterize this scale-dependent bias on all scales and for all different possible configurations of isocurvature and curvature. And so this is sort of enormous parameter space to sample. Whereas really, I only need to know one bias curve, and for example, the standard bias curve in lambda CDM, and then I can use this simple model, like just this perturbation theory calculation, to predict all the other bias curves for all other configurations. And that sort of saves me the need to run an enormous number of simulations. So that's sort of one of the strengths of the separate universe approach. Some more recent results along the sort of same line, we're considering the scale-dependent effects on bias for radiation perturbation. So we have radiation in our universe, the photons, and they affect structure formation on different scales. And really the relevant scale here is the horizon scale. And so these effects are much smaller, and you can only really notice them in sort of earlier times at, or pretty early redshifts for large scale structure, like redshift 2 or something like that. I think the plot here I'm showing is from redshift 1, I think. But you can see that the bias curves are, the differences are much smaller than the previous examples. This is a sort of much more realistic cosmological scenario. And in fact, in order to get these results, to detect these results in our simulation, we had to up the amount of radiation in the universe by a factor of 10 to make this detectable in our simulation. So these effects are actually really tiny effects. And for future cosmological surveys, you'd expect these to be sub% level effects. But they still represent important systematics for really futuristic surveys, which may try to constrain primordial non-Gaussianity, say on the % level. But similarly, we do this, this test of this sort of model by taking the ratio of 2 different bias curves. And you can see that for this orange curve, which is the ratio of these 2 different bias curves, it's relatively independent of mass, and it agrees well with this model calculation, which is the same model as in my previous slide, which is the ratio of power spectrum responses in the separate universe. And so this model has been shown to work really well in a number of different. That was the end of my sort of applications of the separate universe for interesting beyond lambda CDM scenarios. Now I'm going to return to regular lambda CDM cosmology, but look at a different observable. So instead of the abundance of objects, such as voids or halos, instead I'm considering here the statistics, the 1-point statistics of the smoothed matter density field. So this plot at the top here, the black dashed dot curve shows the 1-point statistics of the matter field smoothed over a spherical top hat window at a radius of 10 megaparsecs in the global universe. So this is the probability distribution function of finding a region of fixed size and shape in the universe at a given density. But I can also measure this in smaller patches of my simulation. So I can measure this in subregions, which have some long wavelength density perturbation. So the color of the curves corresponds to the value of the long wavelength fluctuation. So the blue curves are the underdense patches and the red curves are the overdense patches. And you can see that the shapes of these 1-point statistics probability distribution functions are modulated or affected by the presence of long wavelength density modes. And so you get a more sharply peaked to narrow distribution in an underdense patch, which corresponds to a sort of reduced structure formation, and a broader distribution in an overdense patch, which is the enhanced structure formation. And so you can see this response and the fractional difference here is something we can measure in the separate universe. But again, not only can we just measure this using separate universe simulations, we can also model it extremely accurately, actually, in this case. So here, in this slide, I'm showing a top row of plots, which is just the 1-point statistics in the global universe at a few different redshifts, along with this red dashed curve, which is a model that is based on this paper by Ivanov, Kurov, and Sibirikov. They actually do a much more sophisticated model calculation than the simple model that I've used, which is based on a spherical collapse calculation. They consider non-spherical corrections to this in this sort of path integral formalism that they developed. But even in this sort of simple spherical collapse model that I do an okay job at reproducing the peaks of this distribution, but not such a good job reproducing the tails. And in fact, it's on a logarithmic scale. So even near the peak, it looks better than it really is. On the other hand, for my separate universe responses of the shape of this PDF, which kind of has this U shape because I have enhanced clustering, which gives me stronger both underdensities and overdensities on small scales in an overdense separate universe, and gives me this sort of weak negative response because, sharply peaked distribution in an underdense separate universe. So the shape of this distribution reflects the enhanced or diminished clustering in different patches of the universe. But you can see that the model calculation does an excellent job of reproducing the shape of these responses, even in regions where the model doesn't do a good job of reproducing the one-point statistics themselves. So these response observables are easier to model in a sense than their global universe counterparts. And so you might be wondering how to interpret this response of this PDF. And it's like asking the question, if I select regions of the universe of fixed shape and size, but basically select them based on their density. So I sample the universe and I only choose the regions of a given density. Then that gives me some biased sample of the density field. And this response tells me what that bias is. So it's similarly to halos, then if I measure correlation functions among this sort of weird sample of the density field, it would give me biased correlation functions. And this is also something that's sensitive to changes in cosmological parameters. So here I'm plotting differences in this response observable for different cosmologies where I'm varying the neutrino mass. So the curves are based on this model calculation, and I've chosen a reference cosmology where the sum of neutrino masses is 0.06 eV. And so you can see I can fix a smoothing scale, vary the densities of different regions I'm considering, and I get different shapes of this response observable, varying the neutrino mass. Similarly, I can fix the density that I'm considering and vary the smoothing scale, and I get some sensitivity to cosmological parameters, which encodes essentially the way in which structure formation is being affected by the presence of neutrinos. So this may be a useful way of looking at data and trying to constrain cosmological parameters using large-scale structure. Of course, this is in a fairly idealized scenario where I'm looking at the matter field in an n-body simulation. So there's still a lot of work that needs to be done in order to adapt this for more realistic observations. For example, trying to generalize this to maybe a weak lensing scenario where you're probing the matter field, or trying to adapt this further to consider halos and galaxies and one-point statistics among those more complicated observables. So that's future work that I'm still sort of considering how that should be developed. So finally, the last thing that I'll talk about is along similar lines, but from a slightly different point of view. So the one-point statistics I was presenting earlier were looking at regions of the universe of fixed shape and size. On the other hand, instead of doing that, you can allow regions of the universe to vary in shape and size, but try and hold the amount of stuff inside of those regions fixed. And one approximate way of achieving this is through Voronoi tessellation. So these three plots here sort of illustrate what a Voronoi tessellation is. On the left-hand side, I have a slice through a halo catalog. So the blue dots are halos from my n-body simulation. And each cell, which is called a Voronoi cell, contains one halo, and all of the space inside of that cell is closer to that halo than any other halo in the catalog. And that's the definition of what a Voronoi tessellation is. In the middle plot, I'm zooming in to this halo here and its Voronoi cell, and I'm showing the distribution of the matter from the n-body particles from my n-body simulations. And the blue dot here again is that halo, and the size of that dot corresponds to its virial radius. And then finally, in the right-hand plot, I'm showing inside of that halo's virial radius the distribution of the matter from my n-body simulations and the Voronoi tessellation around that matter. So at least for the matter field, since there's all the matter particles from the n-body simulation have the same mass, this is approximately, in a sense, a smoothing of the matter field on an equal mass scale rather than an equal volume scale. So it gives some kind of, so almost like a Lagrangian picture of the density field. So just to give some background of what Voronoi tessellations have been used for in the past, I came to be introduced to them using void finders. So the void finders Veed or Zobov use Voronoi tessellation as an estimator for the density field in order to find minima and find voids. Early work on Voronoi tessellation used Voronoi tessellation for more accurate estimations of velocity fields, actually, in simulations. And the 1-point statistics of Voronoi tessellations have been studied before, and I'm generalizing this work essentially into the separate universe context. So again, just as for the spherically smooth density field, I can compute the 1-point statistic, so the probability distribution function of finding Voronoi cells that have a given density, which is essentially finding Voronoi cells of a given volume. And so for overdense patches and underdense patches, I get different distributions. Again, broader distributions for overdense patches and more sharply peaked distributions for underdense patches. And so you can see there's some characteristic response, which depends on the long wavelength density fluctuations in my sub boxes in my simulation. Similarly, I can do the same sort of thing for the halos, but unfortunately the statistics are much lower for the halos and the responses are a little milder. So it's quite noisy actually, which is I think kind of disappointing. But on the other hand, one nice thing about these results for the matter is it allows me to sort of validate my separate universe approach in a way that I like a lot. So that's the last slide that I'll show here. So when we validate the separate universe technique, testing that we're actually extracting what we're trying to extract using the separate universe method, what we do is we compare with the clustering method. So we take some cross power spectrum of the observable we're interested in, or fluctuations in the observable that we're interested in this case, the shape of the probability distribution itself, and we cross correlate it with the long wavelength matter fluctuations in the simulations, divide by the matter-matter power spectrum and take the long wavelength limit. That's what the clustering bias is. And so that's shown here as this red dashed curve, and you can see it agrees well with this finite difference derivative response from the separate universe method. And it agrees well over sort of this enormous range of densities from 5 or 6 orders of magnitude of density. And the reason why I like this is because when you do this validation for the halo mass function and the halo bias, you're really focusing on the extremely high dense virialized regions, these high density regions. Similarly for voids, you're really looking at the low density regions. And if you do the same kind of validation for the power spectrum, what you're doing is you're binning together overdense and underdense regions because the power spectrum is quadratic in the density fluctuations. Whereas using these 1-point statistics, you can really separate these different regimes of low density to high density and show that these linear responses you get from the separate universe method agree well with what they should agree with, these clustering methods, these sort of biases of these correlation functions, which is what we're trying to calibrate. And so in summary, extracting new physics from large-scale structure surveys requires really accurate and robust predictions for fairly complicated observables like galaxies, voids, and other observables that we have. Whereas the separate universe method allows us to sort of deal with some of these complications by calibrating bias factors, by studying beyond lambda CDM physics through the way that physics can affect the evolution of really long wavelength density perturbations. And we can also model these response observables in ways that are physically motivated from the separate universe point of view. And a lot of these models are fairly successful, are really good at reproducing these beyond lambda CDM scale dependent effects, and also these response observables, such as the PDF response that I just showed. And so this allows us to explore new observable statistics and these sort of generalized biases like the PDF response. And so, yeah, thank you.
Okay, wonderful. Let's unmute and thank Drew. So I guess we have plenty of time for questions, and I have lots of them, but I want to give everybody else a chance to ask Drew questions. So you could just unmute yourself. Jonas, go ahead. I can see you, yeah?
Oh, okay. Thanks. I enjoyed your talk. Thank you very much. About 20-ish years ago, there was a movement that that analysis of galaxy clustering was fractal. The structure was fractal, and galaxies clustered with a dimension of 2 as opposed to 3. I think I was just curious if you had considered that in your work at all, kind of studying that. Yeah,
so my work specifically hasn't focused on this. Definitely on this slide that I showed earlier, showing the sort of applications of the Voronoi tessellation, I have here cosmic web structure. And one of the uses of Voronoi tessellation is to do this kind of characterizing the sort of filaments and domain walls and such stuff like that, to sort of characterize these topological effects and potentially detect, the sort of Minkowski functionals, I think is what they're called. I haven't specifically looked at that myself, but I know that that is something that people use this Voronoi technique to do, and could also be considered from this separate universe point of view. So the statistics, there's actually a lot of information in those configurations of this, topological features of the density field. And so these will be modulated also by the presence of long wavelength modes. And so that is something you could study from the separate universe point of view. It's just not something that I've done yet.
Okay, great, thanks.
So it's an interesting, I guess you talked about advantages of being old. I think this piece, what Jonas talked about, is part of prehistory that we don't teach as students anymore. But in fact, 20-something years ago, people were thinking universe is not homogeneous on larger scales, but rather fractal. And I think more or less that's been dismissed by now. But it's so much that nobody even talks about it. So
okay, I was not aware of that.
Yes,
interesting.
In the late 90s, basically, there was an active debate, right?
Hmm.
Cool. Thanks, Drew. Other questions?
So I can ask, so Drew, so you described how to estimate like these linear density biases using these separate universe sims. So I was just wondering if the same method could be used to estimate other kinds of biases, so for example, like B2, right? So if you, so if you took the difference between like 3 simulations instead of 2 simulations,
yeah,
could you use that to get B2? And then similarly for like, other biases, like the shear bias and so on.
Yeah, absolutely. So let me see if I can zoom out to try and scroll through these a little more efficiently. Sorry, 1 second. So yeah, I will say definitely people have actually calibrated some of these other biases. So in this this other paper here, in this other paper by Chan, Lee, Biaghetti, and Nico Hamas, they looked at the void bias as well, and they actually detected the B2 using the separate universe technique as well. And so I could do that. I typically don't look at higher order biases just in my work. I've been mostly focused on linear biases, but yeah, we typically really run 3 simulations. We run a global universe simulation and then 2 separate universe simulations. So I already have 3 data points that I could use to measure B2. And you could similarly vary the amplitude of the long wavelength mode, and measure a whole bunch of them and try and fit higher order bias coefficients. Also in the bias expansion, you have tidal effects, right? Biases from the tidal field, and there has been a sort of active program to measure this bias coefficient. So far, it's only been successful at measuring shape biases, I think. So biases in the statistics of galaxy or halo shapes. It's tricky. There are a lot of technical details involved in doing these. So the way the tidal effects are done is through anisotropic simulations, right? Where you have different scale factors along different directions. And that complicates the n-body codes. The force solvers have to be changed. And there's many details of the algorithms, like setting up the initial conditions has to be done really carefully because you have these ellipsoidal distortions on large scales. So there's a lot of technical details. I don't think it's fully been worked out to measure the linear tidal bias. Yeah, but that's something people are working on.
Mm-hmm. Okay, great, thanks.
Yeah, I think the people in Fabian Schmidt's group have done work on this and trying to measure some of these higher order biases using separate universe type approaches.
Yeah, that's right.
Right. But I guess the problem is you don't have a homogeneous cosmology, and we don't have an isotropic cosmology. I guess it seems to me it's like a Bianchi cosmology of some sort, isn't it? If you want to think about an anisotropic shear field, right? Yeah.
So it is a little different. Of course, you're really interested, like the effects, like, I mean, it depends on which scale you're interested in, right? So if you're really sort of interested in this sort of quasi-linear regime where the effects are kind of small, they might help you, I don't know, with sort of some effective field theory approach to these kind of bias expansions, then maybe you're really sort of only interested in these sort of perturbative effects of this anyway. So, I mean, the problems that they have, I think, in extracting these results from n-body simulations is convergence. So if you run different simulations with different resolutions, you find different tidal biases. And so they haven't fully resolved that yet.
Interesting.
Hmm.
Wow. So other questions for Drew? Since I don't see anyone else, I can ask a couple of questions. Can you go back to the previous slide? I think was the one before this. No, sorry, before the last slide. I guess you had this response as a function of density.
Oh, yeah.
That was, I guess, towards the end of the talk, maybe 26.
Sure. For the spherically smooth density field or for the Voronoi field?
I think I see there's 27 there. It's slide number 27.
Yeah.
Yeah, that's the one. Okay. So so this is response of the PDF, right, to delta nu or delta V, is that right? So
it's to delta L. L is for long wavelength mode. Delta V is the Voronoi density. So it's really just 1 over the volume of the Voronoi cell.
So I guess good. So the thing I'm curious about is this: there's a huge range here. You're going from 0.1, which I guess is for the voids, but then 10 to the 5, it's like very, very, I guess, the centers of halos or something like that, right? Mm-hmm. So I mean, is that, can you measure things there? Or I mean, it sounds like a weird place to measure PDF. But what are you measuring there?
Yeah, so so I run gravity only simulations. So the baryons are there according to their mass, but none of their baryonic friction, none of the sort of hydrodynamic effects of baryonic physics is going on. And so in these really high density regimes, this would not correspond to realistic structure formation within the presence of baryons. So really I'm only measuring the effects just due to gravitational clustering alone. You'll also notice that there is some discrepancy actually between the clustering method and the separate universe method. And that's actually because in my n-body codes, this is around the regime where force softening is becoming important. And so I didn't actually adjust the force softening in my separate universe simulations to correspond to the sort of same physical force softening in the global universe. And so I think that actually explains some of these discrepancies on these high density regions. So you are really, this is sort of the regime in which I'm questioning the validity of my, the resolution of my simulations.
So this sign change you're saying, shouldn't be taken so seriously at the very high deltas?
That's right. Yeah, I think that has much more to do with force softening.
Yeah, okay.
Yeah, okay, that's very interesting. So I guess another question I wondered about is that have you considered how the properties of halos change in this separate universe simulations, like for example, the concentration mass relationship or just generally the profiles? I guess the simplest thing would be the concentration mass relationship, right?
So I don't. So I, again, in this earlier slide, this one, this group here looked at halo occupation distributions for, so they considered hydrodynamic simulations from the separate universe point of view and sort of calibrated halo occupation distribution functions from the separate universe point of view. And so there are groups working on this kind of thing. As I said before, for the tidal distortions, people have considered shape bias, so looking at different populations of halos selected based on their shapes. So people have looked at these different, definitely anything that's affected by essentially gravitational clustering will be modulated in this way by long wavelength modes. In my paper with Marlena, where we looked at the void bias, we also measured void profiles in the separate universe. And I don't have a slide on that here, but we found modulations in sort of the expected profile of voids based on whether you're in an overdense or underdense patch.
Right. Yeah, I think the interesting thing about this, I was certainly for voids, but also halos is, so in the context of halo models, usually people just assume that the halos are the same everywhere. Their number changes when they look at clustering. But of course, if they're in overdense or underdense region, their profile would change. And that would be, that in some sense, that would be an extra contribution to this.
For sure. And that's also, I should point out this paper that looked at assembly bias from this point of view, because that's also similar, right? So, selecting halos. Yeah, based on their properties. So yeah, there's a lot of work that I think being done along these lines.
Okay, very cool. Other questions for Drew? I don't see anything. Any raised hands? Okay, then wonderful. This was very interesting. Thank you very much, Drew. It was great to catch up. And yeah, and thank you for giving me the chance to introduce you. Actually, I was.
Oh yeah, thank you for that lovely introduction. Yeah,
Okay.
Yeah, and thanks for the opportunity to give this talk again. I'm sorry my advisor couldn't be here, but I was really excited.
Say hi to Marie when you see her next. Hopefully her son